Now let's go back to the simple 4-ply laminate we made in the first video and see if we can find out something about its strength as opposed to its stiffness. Cross-plied demo. 4 plies of unidirectional carbon epoxy. Of course, the strength of the laminate is going to depend, at least partly, on the strength of the individual ply materials. Let's just remind ourselves how those are described. If you remember, we have 5 numbers which describe maximum stress, allowable stresses, and 5 numbers which describe allowable strains, maximum strains. This number is the fibre direction tensile strength. This is the transverse tensile strength. These two are compressive strengths in the 1 and 2 directions, and this is the in-plane shear strength. So let's first of all apply an arbitrary load, in-plane tensile load of 1 megapascal, and see what happens, see how the laminate responds to this applied stress. The first tab gives us information about what's happening on a ply-by-ply basis in the global coordinates and also in the local coordinates. The global coordinates are x and y, so these are the stresses in the x and y directions, and also the xy shear stress for plies 1 to 4. It gets a little hard to see the numbers, so the plot might be a useful option here. You can see that the 0 degree plies here are stressed relatively highly, which is what you'd expect because they are the stiff plies. We also have a local plot. Remember to press the calculate button each time you change any of these options. And again, we can see in the fibre direction the stresses in the outer plies are very high. In the middle plies they're much lower. The strain, as you'd expect, is uniform. That's one of the fundamental assumptions of the laminate analysis, is that in plane tension all the plies experience the same strain. Mid-plane strains and curvatures are also available. We have no curvature because we're not applying any bending moments, and here are mid-plane strains. So how strong is this laminate? Well, if we go to first ply failure, we can run a calculation depending on which failure criterion we want to use. Maximum stress and strain are relatively simple ones. Psi-Wu, Psi-Hill, Hashin are interactive criteria. These criteria at the bottom rely on quite a deep knowledge of what's happening on a microscale in the material. So we'll stick to maximum stress for the moment, run the calculation, and this tells us we have a safety factor of 307 for our applied laminate uniaxial load of 1 megapascal. So that means that the effective first ply failure stress for this laminate is 307 megapascals. First ply failure isn't necessarily the end of the story, because failure is happening in ply 2. That's a transverse ply. That's one of the weaker plies with respect to the applied load. So we would expect the outer plies to remain intact. We can explore that a little bit more with the progressive failure option. Progressive failure will step through incrementally the applied stress and work out stresses and strains and decide whether failure has been reached in the other plies. So let's go back to laminate loads. Let's take a guess at, let's say, 1000 megapascals. So we go well beyond our first ply failure stress. Run the calculation. and we get a tabulated plot of incremental stresses, corresponding strains, and the failure index. And if we zip down here, the first occurrence of failure index equal to 1 is when the transverse plies fail, plies 2 and 3, and that corresponds to 310 megapascals. There's our first ply failure. What we do here is to degrade the properties of the failed plies, but the longitudinal plies are still able to carry stress, and so we can go on down this table, and eventually we find another row in yellow at 730 megapascals, and that corresponds to the failure of plies 1 and 4. That's the two outer 0 degree plies. So we had first ply failure at about 310 megapascals, ultimate failure according to this failure criterion at about 730. On a plot of stress against strain, there's our initial first ply failure point. You can just about see that point there, which corresponds to ultimate failure. Unfortunately, the graph doesn't know when to stop, and it continues plotting in this region here, which isn't terribly helpful. There is actually our ultimate laminate failure.